Hello students, let us discuss polarity of bonds. As we have already discussed the two type of bond, that is ionic bond and covalent bond. Covalent bond is formed by the sharing of electron between the two atoms, and ionic bond is formed by the transfer of electron from one atom to another. But the existence of 100% ionic or 100% covalent represent an ideal situation. But in reality, no bond is completely covalent or completely ionic. That means the covalent bond between the two atoms have some ionic character. That is explained due to this polarity of bond. That means in the case of different atoms, when they are sharing the electrons, in that they develop a partial positive charge and partial negative charge. This is due to the electronegative differences between the two atoms, like in this case of HCl. Chlorine is more electronegative, so it attracts the shared pair of electron towards itself. Therefore, it develops a partial negative charge. But the hydrogen develop a partial positive charge. When a covalent bond is formed between the two similar atoms, which is called as homonuclear diatomic molecules, the shared pair of electron is equally attracted by the two atoms in such cases. As a result of this, the electron pair is situated exactly in between the two identical nuclei. Such type of molecule does not exhibit any poles. That means such type of molecules are called as non-polar covalent bond. Examples are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. But in the case of a heteronuclear diatomic molecule like HCl, here the shared pair of electron will be slightly shifted towards the chlorine because chlorine is most electronegative. So, because of this reason, hydrogen develops partial positive charge, chlorine develops partial negative charge. As a result of this polarization, the molecule possesses the dipole moment. Dipole moment, which can be defined as the product of the magnitude of the charge and the distance between the centers of positive and negative charge. The dipole moment can be found out by, that is, dipole moment is equal to charge into distance of separation. We represent mathematically the dipole moment, that is mu is equal to q into r, where the dipole moment is represented by mu and the magnitude of charge is represented by q and r is the distance of separation. So, the dipole momentum is equal to, that is, q into r. So, this is the formula for dipole moment, that is mu is equal to q into r, where mu is the dipole moment, q is the magnitude of the charge and r is the distance of separation. Here, what will be the unit for this? The unit is generally expressed in d by unit. So, the dipole moment is usually expressed in d by units. 1 d by is equal to 3.33564 into 10 raised to power minus 30 coulomb meter. Here cm that is coulomb and m is the meter. How it comes coulomb meter? Because the formula is dipole moment is equal to q into r. What is the charge of q? Q what is? Q is the charge, and charge unit is represented in terms of coulomb. R is the distance, and the distance in SI unit it is represented in meters. So what is the unit for this? That is coulomb meter. That is represented by 3.33 into 10 raised to minus 30 coulomb meter. That is equal to 1 dBi. So the dipole moment for the molecule is usually represented in dBi. Now let us take some examples and how we represent the dipole moment. In polyatomic molecule, there are more than one bond. So let us take the case of water. In water, there are two covalent bonds. That is, one is here, the other one is here. So in that case, there will be two bond dipoles. And how we represent a bond dipole in a molecule? Through an arrow. And now how we are representing this arrow? That is, for example, the case of HO bond. In this case, because the O is more electronegative, so the arrow should be towards the more electronegative. That means towards the oxygen. That is more important here. Why we have made towards the oxygen? Because oxygen is more electronegative. So the shared pair of electron will be slightly shifted towards oxygen. Therefore, the arrow should be represented towards the oxygen. And we have to keep one line like this. So this is actually representing the bond dipole in a molecule. Since in this molecule there are two bond dipole, so what will be the dipole moment of a molecule? That is the vector sum of these two. So when we make the vector sum, there the direction is also important. So when we make the vector sum of this, it will be have a resultant dipole that is in this direction. So the resultant dipole moment for this is in this direction. From this, we can say that in the case of polyatomic molecules, that the dipole moment is not only depend upon the individual dipole moment of the bond, which is called as bond dipoles, but it depends upon the spatial arrangement of various bonds in the molecule. In such case, dipole moment of a molecule is the vector sum of the bond dipoles of the various bond, and that gives a resultant dipole moment. That is for the case of example water. Now some molecules it is given here. First of all, you should know how to represent a partial positive and negative charge on these. Once you have identified which one have partial negative and which one have partial positive, then you can easily represent it bond dipoles. So let us take the case of water. In the case of water, there is two hydrogen and one oxygen. In this case, which is more electronegative atom, oxygen or hydrogen? Definitely, oxygen is more electronegative. I told you, electronegativity of different atoms you can compare, which is more extremely on the right hand side of the periodic table and which is most on the top side, that will be more electronegative. So definitely oxygen is more electronegative. So oxygen develop partial negative charge and hydrogen develop partial positive charge. So this is the correct representation for this. What about the case of carbon dioxide? In carbon dioxide, two oxygen and single carbon. In compared to carbon and oxygen, which is more electronegative? Definitely, oxygen is more electronegative. So carbon develop partial positive charge and oxygen develop partial negative charge. What about in the case of SO2? Sulfur dioxide. Sulfur and oxygen belong to same group. In that case, which one will be more electronegative? I told you, extreme, top and right hand side will be more electronegative. Since both are in the same group, so oxygen is more electronegative in the case of sulfur dioxide. So It develops partial negative charge on oxygen and partial positive charge on sulfur. What about PCl3? In PCl3, there is single phosphorus and 3 chlorine. Which is more electronegative, phosphorus or chlorine? Definitely chlorine is more electronegative. So it develops partial negative and phosphorus develop partial positive charge. So once you have identified the which is partial negative and partial positive, now you can represent the bond dipoles. For representing the bond dipoles, you have to keep a arrow with a tail. Arrow should always towards more electronegative. Let us try for the case of water. In the case of water, partial negative is on oxygen. So the arrow will be towards oxygen. Here and here. Because there are two bond dipoles. And you have to keep a line on the tail. So this is the correct way of representing the bond dipoles. What about the case of carbon dioxide? In the case of carbon dioxide, because here O is more electronegative, so the arrow will be towards oxygen and here also towards oxygen. Here in the case of SO2, the arrow will be towards oxygen and here also towards oxygen. In the case of PCl3, it will be towards chlorine in this way. And don't forget to keep the tail aligned like this. So this is the correct way of representing the bond dipoles for different molecules. So let us take an example like CCl4, CH4 and CHCl3. In the case of CCl4, arrow will be towards chlorine because chlorine is more electronegative, but in the case of CH4, the arrow will be towards carbon because carbon is more electronegative than hydrogen. But in the case of CHCl4, when you look at here the bond dipole, in this case, the arrow will be towards chlorine because when you compare chlorine and carbon, the chlorine is more electronegative. But when you take the case of hydrogen and carbon, which is more electronegative, in that carbon is more electronegative. Now look at the arrow. In this case, the arrow is on the same side direction. So there will be a net dipole moment in this direction. But in the case of CH4 and CCl4, the net dipole moment, that is mu is equal to 0 here. Since the resultant of the two bond dipole get cancelled by other because of the same magnitude of bond dipoles at the direction. Because of the direction, the resultant dipole will be get cancelled. So there will be no net dipole moment for the case of CCl4 and CH4. Let us take the case of example BeF2. BeF2, when you compare the electronegativity, fluorine is more electronegative. So the bond dipole will be in this direction, that is towards fluorine. When we look at the structure here, the two bond dipoles are in equal magnitude because same type of bond is BeF2, BeF, same type of bond. So the magnitude of this bond dipole is same, but the direction is opposite. That is one on this direction, other is on this direction. So what we can say is same magnitude but opposite direction. Since the dipole moment of the molecule is the vector sum of this. It is a vector sum. So definitely what happened, that it will be have net dipole moment will be equal to 0. So what we can say that in the case of BeF2, the dipole moment is equal to 0. Why? Because the two equal bond dipole but in the opposite direction. So it will cancel each. So this will result in the it results in the zero dipole moment for the molecule. So what we can say, the dipole moment in the case of BeF2 is equal to 0. Let us take the case of BF3. BF3, here the bond dipoles are represented. It will be towards fluorine because fluorine is more electronegative. Here the angle between is 120 degree angle. So the resultant dipole moment of these two bond dipole, that is the resultant of these two dipole, will be in this direction, and that is actually opposite to the bond dipole of a other bond. So that will cancel each other. So what we can say, that the vector sum of these will be equal to 0. So the dipole moment for this molecule, that is BF3, is also equal to 0. So in this case, which we have already discussed, because here the bond dipoles which we have represented here. So what will be the vector sum of this? Because this type of structures are called as ideal structures. Ideal structure means which have same type of bond dipoles, same bond dipoles, and because they have perfect structure, that is a tetrahedral structure, in such case the bond dipole will be equal to 0. So bond dipole equal to 0 here, it is equal to 0 here. But in this case, because this is different from other three, because other three are CCl bond dipole, but it is CH bond dipole. So one of them is different. So in that case, the net dipole moment will not be equal to 0. So in the case of water, here the two bond dipoles are there, that is one on this direction and one on this direction. So what will be the vector sum of these two? The vector sum of these will be, gives a resultant dipole that will be in this direction. Its value is equal to 1.8 dBi. That is the vector sum. That is the value we got from the vector sum of these two bond dipoles. Let us talk about an interesting factor in this molecule, that is about the bond dipoles. Here, in the case of NH3, that is ammonia, NF3, that is same structure as like ammonia, that is 3 bond and 1 lone pair. Look at the structure, both the structures are same, that is both have 3 bonds and 1 lone pair. Now let us represent the bond dipoles for each. In the case of ammonia, because nitrogen is more electronegative than hydrogen, so the bond dipole we can make in this way, that is towards nitrogen, because there is 1 lone pair here. So the orbital dipole due to the lone pair, we can say it will be in this direction, because lone pair, therefore the direction will be in this way for the case of lone pair. In the case of NF3, when you compare the electronegativity of nitrogen and fluorine, definitely fluorine is more electronegative. Since here also 1 lone pair is there, therefore the lone pair, it have a orbital dipole, that is due to lone pair. So that will be in this direction. And nitrogen and fluorine is more electronegative, so the bond dipole will be in this direction. Now, in this case, 3 bond dipoles are there in the case of ammonia, and all having the direction towards nitrogen. This is also toward nitrogen, that is in this way. Here. All bond dipoles are towards nitrogen. So what will be the resultant dipole? The resultant dipole will be in this direction. And for the case of NF3 will be towards downward. Look at here why it is upward. Why it is upward here, the resultant? Because the 3 bond dipoles are facing towards the nitrogen. Therefore, the bond dipole will be, the resultant bond dipole will be in the same direction, that is upward. But in the case of resultant bond dipole, in the case of NF3, look at here, in all these cases, the bond dipoles are towards fluorine, that is downward. So here the resultant dipole will be, of 3 bond dipole will be downward. So this is shown clearly by giving the different colors here. So the blue color arrow, it is representing the resultant dipole moment, that is the resultant of 3 bond dipoles is the represented here in blue arrow. Now look at here, definitely the resultant dipole of 3NF bond dipole will be greater because fluorine is more electronegative in compared to hydrogen. So definitely the resultant dipole for this case will be greater than the case of NH3. But still here the orbital dipole and the resultant dipole both are in the opposite direction. So the net effect will be lesser. But in this case, the resultant dipole and orbital dipole, that is both in the same direction. Look at here how it is, this and this in the opposite direction, that is the orbital dipole, and resultant dipole is in the opposite direction. Here orbital dipole, resultant dipole both are in the same direction like this, and here both are in the opposite direction. So definitely the net effect will be lesser. So for this reason we can say that the value of dipole moment for the NF3 is this, and for this ammonia is this. So what it shows that even though fluorine is more electronegative than hydrogen, but still the resultant dipole moment in ammonia is greater than in compared to NF3. So that is the reason which we have discussed. It is very important question which is usually asked in the exam. So in the textbook, some molecules are given and their bond dipoles are given. With the help of bond dipole, we can predict the geometry because as shown here, in the case of diatomic molecule, the geometry will be linear. But in the case of a polyatomic molecule, the value of dipole moment shows the shape. If it is equal to 0, in the case of carbon dioxide, it is equal to 0. What it shows that the structure is linear. Why? Because when it is having a linear structure, then both the bond dipole get cancelled because both will be in the opposite direction. So it have the bond dipole, that is the equal to 0. So the dipole moment for the carbon dioxide molecule is equal to 0 because the two bond dipole will be having same magnitude but in the opposite direction cancel each other. So the net dipole moment is equal to 0. So it shows that its structure is linear. So this fact is very important to predict the shape of the or geometry of the molecule. But still there are some concept which is explaining the shape of the molecule or the geometry of the molecule that we'll be discussing in the next video. So this is all about the polarity of the bond. It is one of the quite important topic for the exam. So this is all about this video. Have a nice day.